Hello everyone, this is Abhinav and today we'll be discussing the 19th problem from the CP-31 sheet by TLE Eliminators under the 1500 rated problems. Let's begin. We'll move on to our CP-31 sheet. We can see that the 1500 rating mark is checked. Let's move on to the 19th problem, which is count subrectangles. Okay, so let's read the problem statement first. So we are given an array A of length n and array B of length m, both consisting of only integers 0 and 1. Okay, so consider a matrix C of size n cross m formed by the rule Cij is Ai into Bi. Okay, so you need to consider a matrix C which is formed from these two, array A and array B, such that Cij would be Ai into Bj. Okay, this would be the element of the matrix. It's easy to see that C consists of only zeros and ones. Okay, so if A and B consists of only 0 and 1, then the product of 0 and 1 would be 0, 0, 0 would be 0, 1, 1 would be 1. So the product would always be zeros and ones only. Okay, so it's quite clear. How many subrectangles of size K consisting only of ones are there in C? Okay, so what we need to find is how many subrectangles which have a size K. That means the area of the subrectangle should be K and it should consist of only and only ones. So how many such subrectangles exist in the matrix C, that we need to find. Okay, and a subrectangle is an integer of consecutive segments of rows and columns. Okay, I hope that is clear. The size or the area of subrectangle is the total number of cells in it, which would be the length multiplied by the breadth. Okay, and this subrectangle would always be like, it would have integer lengths and breadths. As you can understand, it would consist of a segment of rows and a consecutive segment of columns. So I think if that is clear, then let's look at the first example. So in the first example, we have something like this. Okay, let's move it there, we'll understand. So if we see the first test case, we have something like this. This is n, this is m, this is k. Okay, this is array A, this is array B. So what would be the array C that we would form? So this is our array A, this is our array B. So the matrix C would be something like, okay, so the matrix C would be basically A cross B. So you can say in left side, let's say in the first index, this is, let's say, I and this is J index. Okay, so in I it would have AI. So Cij of the matrix is given as AI multiplied by Bi. That is what we are given. Okay, so in this side, let's say we have the array A and this side we have the array B. So then this first element, if we index them with 0, 1 and 2, then here we would have 0, 1 and 2 as the indexes. Here we would have 0, 1 and 2 as the indexes. This would be the matrix we would have. And what would be the elements of the matrix? At position 0, 0, we would have A0 multiplied by B0. So 1 into 1, that would be 1. At 0, 1, we would have A0 multiplied by B1. So 1 into 1 would be 1. Then again 0 multiplied by 2, A0 multiplied by A2, 1 into 1. This would again be 1. Okay, and then this A1 would be multiplied by all the three. So 0 multiplied by 1 would be 0, 0, 0. So this row would be completely 0. And then here we have 1 multiplied by 1, 1, 1. So this row we would have all ones. Okay, so I hope you have understood how the matrix C is formed. Now in this matrix C, you need to compute how many subrectangles of size 2. So K is given as 2 here. So the area of the subrectangle should be 2 and that subrectangle should consist of only and only ones. Okay, so possible rectangles, this is one possible rectangle. Okay, so this has an area of 2, there are 2 cells in it and both of them are 1. So this is one possible subrectangle that we can have. So we need to just count how many such good rectangle or such valid rectangles we can have. So this is one, then this could be another. Okay, so for this subrectangle, it has 2 cells, both of them are 1. Okay, then this could be one possible subrectangle, this could be one possible subrectangle. Okay, so these two are also there. Other than that, other than these four, can we have any other subrectangle of size 2? Maybe if we consider this subrectangle, it has a 0, or if we consider this subrectangle, it has a 0. So all these like vertical type of subrectangles would have size, would have a 0. So only valid cases are these four. Okay, so for this case our answer would be 4. There are 4 valid subrectangles with all ones. Okay, so this was the matrix that we had and our answer was 4. Okay, I hope the problem is now clear what we need to do. So how do we solve this problem optimally? So for that, first let's look at the constraints of the problem before moving on to the solutions. First you should look at the constraints to understand what complexity is okay for us. So n and m are up till 40,000. Okay, so we are given that n is up till 4 into 10 to the power 4, m is also up till 4 into 10 to the power 4, and the k given to us is up till n into m. So the k can be n cross m, which can be 16 into 10 to the power 8, or we can say 1.6 into 10 to the power 9. Okay, whatever you wish to say. So these are the constraints on n, m, and k. So what would be, we can say, what time complexities would be acceptable looking at these constraints in terms of n, m, and k? What we can say that if we have something like an order of n, then 4 into 10 to the power 4 is always fine. Something like order of m would also be fine, 4 into 10 to the power 4. But if we have something like order of k, then 1.6 into 10 to the power 9, this won't be fine, because in 1 second we can have only 10 to the power 8 operations. So this would give us a TLE, but we can have something like this k was actually n into m, the square of n and m. So if we have something in order of square root of k, then this would be fine. Okay, so we can say that we need to have some time complexity, something of the order of n, m, or root of k. These all are fine, and we can also have something like all of them, n plus m plus root k. That would also be fine, but we cannot have the product of any two of them, or n, or all the three. Okay, we cannot have something like order of n into m. Okay, something like order of n into m. These all would exceed our time limit. Okay, so this we can say are our expected time complexities. Okay, these are our expected time complexity. Okay, this is one of the, you can say, the combination of all of them. So we need to solve the problem in something which is linear in n, m, and square root of k. Okay, we cannot go up till the whole order of k. Now keeping this in mind, how do we solve the problem? So what we are given here, let's try to think. Okay, let's think in this example. So what we are given here, in this array C, we need to find some subrectangle which have all the ones. Okay, let's say if we have any one subrectangle which have all ones, this subrectangle has all ones. What can we say this, like, obviously you cannot form this whole matrix C, because forming this whole matrix C would take an order of n into m time in itself. So that would give us a TLE. So it's not possible to actually form this matrix C and then find our answer. First thing is that. So you need to only look at this array A and B and then imagine whatever matrix C we would have, according to that how many such subrectangles exist with the given problem that you need to find. So you cannot actually form this C. So let's see what we need to find in terms of the array A and B only. So we need to find a subrectangle which has all ones in it. When would it happen that the subrectangle has all the ones in it? What would be what values of array A and array B would it take? So if we look at this subrectangle, this one is formed by this second index of array A and first index of array B. These two are forming this one, and this particular one is formed by the second index of array B and the second index of array A. Okay, so this formed the first one, this formed the second one. Okay, so they together formed the subrectangle of size 2, this subrectangle of size 2. Okay, if we look at, let's say, this subrectangle of size 2, okay, then this second index from array A, 0th index from array B, they formed this one, and this one is formed by second index of array A and first index of array B, which is this. Okay, so these two formed this subrectangle. So we can say they formed this subrectangle. So what you can see, again for this also, if you would if you try to find, then it would be 0th index of array A, and these two for array B would be for this, and for this it would be 0th index of array A and these two of array B. So basically you can clearly see, whenever you have a subrectangle, let's say that subrectangle has a length L and a breadth B. Okay, so L into B should be K, that's the first thing. Okay, so because the area of the rectangle is K. Now, but if this subrectangle has a length L and a breadth B, the length is actually formed by the array A and the breadth is actually formed by the array B. That means there should be L number of consecutive ones in array A and B number of consecutive ones in array B. That's what should satisfy in order to form a subrectangle of size K. So basically for this subrectangle, it has a length 1 and breadth 2. That means there is one consecutive one in array A and two consecutive ones in array B. For this subrectangle, like this and this was for this one, and for this subrectangle, there is one consecutive one in array A and breadth is 2, so two consecutive ones in array B. So basically we can say that whenever we need to find a subrectangle of size K, okay, this first of all we can partition this K into different subrectangles. Okay, let's say if K is 12, so what all dimensions of subrectangles can we have? We can have a 2 cross 6 subrectangle, or a 3 cross 4, or a 6 cross 2. These are the possible dimensions of the rectangle that we can have. So we can say, like, we can calculate our answers separately for all these. If we calculate separately for all these, then the number of subrectangles with dimension 2 cross 6 which satisfy our condition would be the number of number of such instances where in array A we have two consecutive ones, and number of such instances where in array B we have six consecutive ones. They together would form the subrectangle of size 2 cross 6. So we can say that in whatever the complete matrix C we have, in order to form some subrectangle of size 2 cross 6, it should be something like this, where length is 2, breadth is 6. So these two should be 1 in A and there should be 6 consecutive ones in B. Okay, so let's say we have a subrectangle here and a subrectangle here, and then let's say we have a subrectangle here. So in array A we should have a 1 and 1 here, array B we should have 1 1 1 2 3 4 5 6, and this should also be 1. Let's say this is 0 1 1 0. Okay, and let's say this is 0 0 1 0 1. Let's say this is our array A and this is our array B. Then in that case, for this given array A and this given array B, when would we form a subrectangle of size 2 cross 6? When in array A we have two consecutive ones, array B we have six consecutive ones. Okay, so this together would form one subrectangle, and then a different pair of six consecutive ones in array B and maybe the same pair of consecutive ones in array A may form a different subrectangle. Again, this same pair of six consecutive ones in array B can form a subrectangle with this also, and it can form a subrectangle with this also. So here if we count in array A the number of such instances where we have two consecutive ones, it is 1 and 2. There are two instances where we have two consecutive ones. If we count in array B the number of such instances where we have six consecutive ones, then that would be 1 and 2 instances. So that would also be 2. So the total number of subrectangles that we would have would be 1. It would be 1, 2, 3, 4, which is actually 2 into 2. Okay, so I hope this logic is clear to you. So basically we can say that the number of subrectangles with dimension 2 cross 6, I'm telling, let's say FA of 2 cross FB of 6, where FA is a function which returns the number of instances where we have two consecutive ones in array A, and FB6 returns the number of such instances where we have 6 consecutive ones in array B. Okay, so if somehow we can calculate these two functions, okay, then we can just directly say for 2 cross 6 our answer would be this multiplied by this. For 3 cross 4 our answer would be FA of 3 multiplied by FA of 4. For 6 cross 2, FA of 6 multiplied by FB of 2. Okay, so if this conclusion is okay to you, okay, it's getting a little cumbersome, so I hope this explanation was clear to you. So I'll write this. Okay, so for any number k, what we can say, first of all, find all the basically dimensions that we through which we can form this k. So how many such different dimensions would exist? If you try to think, it would be the number of factors that k has. Okay, you can put every factor as a L, and then the other part would become your B. So how many factors does a number have? So how much time would it calculate to find all the factors of a number? You know the algorithm. To find all the factors of a number would take order of square root of k time. In square root of k time, we can just compute all the factors of k. And if we can compute all the factors of k, then for every factor, if I is a factor, then k by I would be the other dimension. So then the number of this different factorization that could be computed in order of k. For every factorization, we'll say our answer is FA3 into FB3. Now we need to pre-compute the values for FA and FB. Okay, because if here we are now going to compute these values, that would add, even if that is taking order of n time, root k into n would give us a TLE. So what we can do is we can pre-compute the values of FAK. So we would have to pre-compute the values of FAK for like FAX. Let's say I'm not using k here, I'm using x. Okay, so we need to pre-compute the values of FAX for all x from what can be, for what all x can exist here. Now if you look at here, the factors may go up till k, but what does actually this FA is, what this FAX is actually, it is number of you can say the number of subarrays of size k, of size x, having all ones. This is what FAX means, the number of instances where you have x number of ones. That means the number of subarrays of size x having all ones. That's what our FA of x is. Okay, now what can be the range of x now? So the size of the subarray can at max, for array A, it can at max go to the size of the array, which is n. Okay, so this would be computed for all x belonging from 0 to n only. Okay, we don't need to compute for more than n. For FA of x for x greater than n, what would be what it would be? It would be directly 0, because there won't be any subarray of size more than the size of the array, obviously. So this value would be 0 automatically. So basically we need to just pre-compute FAX for all the x up till n. And same way for FAB, we need to pre-compute for all same way for FBX, we need to compute for all x less than equal to m. M is the size of array B. So now how do we compute this function? That's the next problem to us. Now, this fax, the x is going up till n and this is going up till m. So we need to compute these in order of n and order of m only. Okay, then we would have order of n time complexity is fine, order of m pre-computation is fine, and then once these pre-computations are done, an order of root k final computation would also be fine. So this time complexity would be fine. Now the main problem that we are left with is how we can compute in order of the size of the array this function, number of subarrays of size x having all ones. Okay, so let's take this as a different problem and try to compute. So let's say you have an array A. Now this array consists of only zeros and ones. Okay, let's say we have something like, let's say we have an array A something like this. Let's try to compute our fax. Okay, what would be fa0, fa1, fa2? Like fa0, like size 0 doesn't like make a sense. It would be from 1. Okay, so fa2, fa3, fa4, fa5. Okay, these all we need to compute up till it would go whatever is the size of the array. So let's start computing. Okay, now we know we need to just do a order of n traversal only. We cannot do more than that. So let's try to do a traversal in this array and start computing these values. So when we find a 0, here we cannot make any array of size 1, 2, 3, anything having all ones because this is 0. Okay, let's move ahead. We have got a 1. So now till here, if you observe the array till here, then we have a 1. So the number of consecutive, so if you want to have a subarray of size 1 having a 1, there you would do a plus 1 to this fa1. Okay, because this one would be one valid subarray of size 1. So a plus 1 to that. Next you move to the next one. Then you would say that this one again would contribute. Okay, then when you move to the next one, you would say that this one individually would contribute to a subarray of size 1. So plus 1 there, and these two ones together would contribute to a subarray of size 2. So a plus 1 in fa of 2 as well. Okay, next you let's say move to this one. Now this one individually would contribute a plus 1 to a subarray of size 1, and these two together would contribute a plus 1 to subarray of size 2. Okay, and these three together would contribute to a subarray of size 3. So a plus 1 there. Next, let's say you move to this one. Okay, this individually would contribute a plus 1 here. This individually would contribute a plus 1 here. These two together would contribute a plus 1 here. These three together would contribute a plus 1 here. These four together would contribute a plus 1 to fa of 4. So can you observe what is happening here? Okay, let's say after that you move to 0. If you move to 0, then any subarray ending at this is not going to contribute anything to your consecutive subarrays of having only ones because it has a 0. So after crossing this, your answer remains the same. Then again a 0, you can move ahead. Then when you get the next one, now this one would individually contribute a plus 1 here to array of size 1, but these two won't contribute to 2 because here you have a 0. So this would only contribute a plus 1 here. Then next when you move to this one, then this one would contribute a plus 1 here and a plus 1 here. So after this, like observing this, what you can understand that when you were on the first one in a series of consecutive ones, it contributed a plus 1 to 1. When you move to the second one, it contributed a plus 1 to both of 1 and 2. When you move to the third consecutive one, it contributed a plus 1 to both 1, 2 and 3. When you move to the fourth one, it contributed a plus 1 to all the first 4 values. And then when you move to a 0, it all got reset. And then again, when you got a 1 again, it started with a plus 1 here, next one, a plus 1 to the first 2. Then this would again reset, then this one would do a plus 1 here. So this way you would get, so when you add all these up, you would get your final value of FA1, FA2, FA3, FA4. FA1 is 1, 2, 3, 4, 5, 6, 7. So there is 1, 2, 3, 4, 5, 6, 7 subarrays of size 1 having ones. FA2 is 1, 2, 3, 4. So 1, 2, 3, 4. These 4 are of size 2. FA3 is only 2. So these 2 are the FA3. FA4 is only 1. This is the only one FA4. FA5 would be 0 because there are no consecutive 5 ones. Okay, so now how do you do this computation optimally in order of n? If you do like this, then when you move to the third one, if you do a +1 to all the 3 of them, that would again, if you have all the ones, that would take an order of n time in doing a +1. Overall, it would become order of n square. If you have like all the ones, let's say, then doing a +1 to all the items every time would give you an overall complexity of order of n square. How can you reduce it to order of n is using a concept of difference array. So what you need to do is you need to do a +1 in all the in a range of values. Always you can see here you did a +1 in this, then you did a +1 in the first 2 values, then a +1 in first 3 values, then a +1 is in first 4 values. So this thing you can do through a difference, through the difference array concept. If you know about that, what you can do is when you have to do a +1 in this range, you can like either you can do through a prefix sum way or a suffix sum way. Here we have to do a +1 in all the in a whole prefix. So we would like finally what we would do is in our difference array we would do the suffix sum. So if you are taking the suffix sum finally, then doing a +1 at 4 means doing a +1 to the whole prefix. Doing a +1 to 3 means doing a +1 to the whole prefix up till here. Whatever we are doing there, finally we'll take a prefix array. Like what I'm telling is, I hope if you know about the difference array concept, this would be quite simple, but still I'll explain once that in your FA array, initially you would have index 1, 2, 3, 4, 5, 6. Okay, so first when you move to the first one, okay, you need to do +1 in this range. So what you would do, you would do a +1 here. Okay, then you move to the second one, you need to do +1 to both of these values, but you will only do a +1 at 2. Okay, then you move to this one, you need to do +1 to all the 3 values, but you will only do a +1 to this, because this one would actually do a +1 to all the 3 when we finally take a suffix sum of this array. So then this would do a +1 here. Okay, then we have 0, 0, then this one would do a +1 here. So a +1 here, this one would do a +1 here, then a 0, then this one would do a +1 here. So finally what we got in our FA array is, here we got a +3, here we got a 3, here we got a 2, and here we got 1 and 1. Finally when we take the suffix sum of this, okay, so these would be 0. When we take the suffix sum, after the suffix sum, what would happen? This array A, this would be 0, 0, 0 only. Then 0 plus 1 would be 1. Then 1 plus 1 would be 2. 2 plus 2 would be 4. 4 plus 3 would be 7. So this is what we would get finally in our array A. What we were getting, 7 here, 7, 4, 2, 1. Okay, so 7, 4, 2, 1 we have got. So I hope you understood this difference array concept. So after applying this, through this method we can compute FAX and FBX in order of n and order of m time. After that, through this method, through the factorization method in order of root k time, we can compute our final answer. And once we have computed our final answer, our job is done. Overall time complexity would be order of n plus m plus root k. Okay, so let's move to the code part to understand how we are coding it. Okay, so first of all, I have defined my int as long as my final answer may exceed the range of int. So all the int that you see in my code is actually long. Okay, so in my main function, I take the input n, m, k and the two arrays a of size n and b of size m. Once that input part is done, then I'll pre-compute my array fa, which would have a size up till n. Okay, so n plus 1 is the size, so it would have indexes up till n, and fb would have indexes up till m. So I initialize them with 0. I maintain a variable c to count the number of consecutive ones we have currently. So I start with the first index. If ai is 1, then we do c++. Okay, so whenever I encounter a 1, what I'll do, I'll start with c equal to 0. When we encounter 1, we do c++. Okay, so the number of consecutive ones we have is 1, and I'll do fa of c++. Okay, as we did. So here we do a +1. Then next one, then when we have c becomes 2, in fa of 2 we do a +1. Okay, so this way whenever till we have consecutive ones, c would be become fa of c++. Whenever we encounter a 0, this c would get reset to 0. And whenever we encounter a 0, c would get reset to 0. Then again the 1 would make c to start with 1, not with after 4 we would have a 5 if we don't reset. Okay, so with this algorithm, your initial FA would be computed, then you reset C to 0 and compute the same thing for array B. You do the same thing for array B and compute your FB. Now, in this initial FA and FB, what you need to do is you need to do the suffix sum so that you get the actual values of FA and FB. So we do the suffix sum. FA of I is FA of I plus 1 plus FA of I. So plus equal to FB of I plus 1. So once we have done the suffix sum, we have finally computed our FA and FB. Okay. So once this FA and FB are computed, what we need to do is factorize this K, and for all the factors compute this product, add this product to your answer. So we initialize our answer with 0. We need to find all the factors. So I start with I equal to 1, I into I less than equal to K, I plus plus. So we are going up till square root of K, and if K modulo I is 0, if I is a factor of K, then J would be the other factor. Okay, so if we have I as one of the factor, then the other factor would be J. So if I is 2, J would be K by I, which is 6. So now we would what we need to add to our answer is we need to add to our answer fa of I into fb of J. That is what we need to add to our answer. Okay, but first of all we'll have to check whether this I is less than equal to n or not. If this I is already greater than n, then it would be 0 only. So if I is less than equal to n and J is less than equal to m, then only we'll add fa of I into fb of J. Otherwise this would exceed our index range. Okay, and the value would be 0 otherwise. And this is for when 2 was a factor and when 6 would be a factor. So if we have calculated for 2 cross 6, we also need to calculate for 6 cross 2, because if we are going up till square root of 12, we won't go to 6. Okay, for the all factors algorithm, when you get 2, this 6 is K by I. So you need to also compute your answer for fa of J multiplied by fb of I. Okay, so we'll also add fa of J multiplied by fb of I. We'll also add extra check that I is not equal to J here, because in case when K is 9, then we would have a 3 cross 3 factor. So when I is 3, J is 3, we won't compute again for 3 cross 3. Okay, so if I and J are equal, we won't add this again. Okay, so only when they are unequal and J is less than equal to n and I is less than equal to m in this case. Okay, so once this particular thing is added, we have got our final answer. We can print it. Okay, so I hope the code is clear to you. If you look at the time complexity from the code, then this input part, taking array A and array B, this is order of n time, this is order of m time. We have found the two vectors. This is running order of n times. Okay, this loop is running order of m times. Okay, and these two loops are again running order of n and order of m times. Okay, now this is running order of square root of k times. Inside that we have only if else conditions. So this is running order of square root of k times. Okay, so finally we can say what is our time complexity. Our time complexity is order of, we have n, m and square root of k. Okay, so n plus m plus square root of k is our time complexity. If we analyze the space complexity, our space complexity would be, we have this array A and array B of size n and m. these two FAFB are also size n and m, and then other than that we don't have any other vectors, so we can say our space complexity would be n plus m. Okay, so I hope everything is clear about this problem. This was a really nice problem of number theory, which with multiple concepts used like difference array as well. So I hope you liked the explanation. Thank you very much for tuning in.